In this video I'm going to talk about electrophilic addition mechanisms for AQA AS Chemistry. In 3.2.9 Alkenes is a section saying that you need to know addition reactions of alkenes, understand the mechanisms of electrophilic addition of alkenes with HBr, H2SO4 and Br2. These are the three examples I'm going to use in this video for symmetrical alkenes. The first equation is ethene with hydrogen bromide, so HBr, goes to bromoethane. The first step you've got to show that the carbon-carbon double bond breaks. It's because the electron density is drawn to the electropositive hydrogen, which is less electronegative than the bromine. So then you've got this symbol above, which means electronegative or more electronegative. These arrows represent where the electron densities are drawn to. So this is drawn to the hydrogen, and then the bond between the HBr is drawn to the electronegative bromine. The HBr is your electrophile. When this separates, heterolytic fission occurs. So example 1, in HBr, you can imagine the bond represents the electrons. They completely separate going to the bromine, as you can see there, and then you get left with your negative ion and then 2 electrons to show. The second step is to show that your hydrogen has joined on, as you can see in red, and a carbocation is left in its place. This isn't just any carbocation, it's a primary carbocation. So if you do not know what carbocation is, it is an organic ion in which one of the carbon atoms has a positive charge, which I've represented in a little circle and highlighted it so you can see. A primary carbocation is when there's just one carbon attached to the carbocation. A secondary is when there are 2, and then tertiary is when there are 3 around it. You might be wondering why I've drawn a CH3. Some people might think I'm showing that the bonds to the hydrogen, but it's not. In the exam it is acceptable to write CH3, or if you want to be careful you can write a H3C to show. Okay, so the second step is to show that the negative electron density in the minus ion, is drawn to the positive carbocation. So can you imagine positive attracts negative, just logic, and then that is then creates bromoethane. As you can see, the hydrogen from before and the bromine attached to it. I also draw vertical structures because it's just easier to show where your arrows are going rather than it being horizontal. The second example is ethene with sulfuric acid. You draw your sulfuric acid like this. You understand why when I go through it. To produce ethyl hydrogen sulfate. Step 1 again is to show that the carbon-carbon double bond breaks. This is because the electron density is drawn to the electropositive hydrogen. The OSO3H is electronegative. This again is your electrophile. And I've just said then, before I mentioned about the arrows touching the bond, but in this mechanism you've got to always show that between this bond, the arrow's got to go directly up to the oxygen only, not to the SO3H, not to the H, not to the end. It's always got to go back to this oxygen because this is the one that's electronegative to what the hydrogen's bonded to. The second step again is to show where your hydrogen's gone and that your carbocation, your primary carbocation, is left behind. So the lone pair and the minus must always be on the oxygen. Little note there. So here is where your negative ion is created from the electron density from heterolytic fission. So this is drawn to the carbocation. So this electron density is drawn all the way over to the positive. Then this produces ethyl hydrogen sulfate. As you can see, the vertical structure again, it's just the same as the horizontal. You can draw it either way, but I just prefer it this way. This reaction, you might be asking the exam, what can this reaction be used for? Well, if you follow this reaction through, it's a process used to make ethanol, which I'll cover later on when we cover alcohols. The ethyl hydrogen sulfate is used, added to water, which then produces ethanol and sulfuric acid back. I wrote here that the sulfuric acid acts as a catalyst in this reaction. You might not understand why now, but you will later on. But it's simply because catalyst gets used up chemically, but then gets replaced at the end. It doesn't get lost, it doesn't change into anything else. It appears at the beginning and again returns at the end. Okay, so the third example is ethene with bromine. You might find this a bit difficult to grasp because it's a bit, okay. To produce 1,2-dibromoethane. The first step, again, is to show the carbon-carbon double bond breaks. So your arrow showing your electron density is drawn to, now this is the tricky bit, the electropositive bromine, which is less electronegative than this bromine, which is electronegative. This is an induced forced electrophile. Br has an electronegativity of 2.8, so you'd assume that the Br to be nonpolar. However, in close proximity of the carbon-carbon double bond, a temporary dipole is induced, so the electron density is shifted to one side, basically repelled, making it an induced electrophile. So, when in the exam, when asked for the mechanistic equations, you must always show that this Br2 is in close proximity. You could write that on the side even, just put in brackets in close proximity, and then write induced electrophile. These electrons repel, and then this density, so before your electrons are pushed over to one side, that's why that's electronegative. The second step again is to show the bromines attached onto the top carbon, and then there's your carbocation attracted to the bromine ion, the negative one. So negative attracts to positive, which is your carbon cation, which is the primary one, and then produces 1,2-dibromoethane. I hope this has helped quite a bit because I just find it easier to cover stuff in a little flowchart like this. If you'd like to download this, I'll put a link up for Get Revising or some form of PDF. Thanks. Bye.